Okay, we're going ahead and talking about math acceleration, and I'm going to be recording this for those of you who cannot attend, but if you're attending, that's great. Um, we're going ahead and talking about virtual reality. I guess those goggles that people wear, and then simulation, and that matrix math that you're learning about in EET 310. So let me go ahead and share with you a short video that I created a little while ago, and then we'll talk a little bit more about what that means in terms of math acceleration and engineering technology with regard to electronics moving forwards. So I'm going to go ahead and share my screen. And let me go ahead and start this video. Hi. Some students have talked about the simultaneous linear equations that we're working on for multisim or simulation of electronics, and how we go about analyzing large circuits and figuring out their functions. But also, students are also very interested in other kinds of simulation. For example, virtual reality, those 3D goggles and rendering images in 3D projected onto a 2D screen that you're watching. So let's go ahead and take a look at something along those lines. I'm going to go ahead and share my screen. And here you're looking at a 3D rendering program. This one is called MeshLab. It's a free 3D rendering program. And it's particularly intended to go ahead and clean up 3D scans. So you might take an object and then scan in all the points so you can print it on your 3D printer. But you might have a lot of errors. So that scanning might have a lot of bumps and holes and things that are just incorrect scans, and you need to touch them up. So this program allows you to look at the actual dots that were captured. And in this case, here it's a seashell. These are the vertices, they're called, actual dots in 3D space. So each one of these dots has an X, Y, and Z location. So we can go ahead and, if you will, connect those dots, and we can form a mesh that really is basically, in this case, it is shaded with a lighting algorithm, just to make it a little bit easier to see. But it's basically just the lines that connect all the dots were drawn in. And then we can go ahead and apply a color according to the angle of the lighting that's striking the object. You can go ahead and apply a color. There's also some other mathematics that are taking place here that are going ahead and seeing which shapes are occluded. For example, you can see that second swirl, but when I turn it here, now it's occluded or hidden by other surfaces. Whereas if I went back to mesh mode, you could still see them all, just as you could see them all if they were just dots. But when I'm going ahead and adding that filled in color, I need to know which parts are occluded. So it's a different mathematics for that. And then finally, we can smooth it so it looks a little bit more realistic, like a shell. Then we can go ahead and export that. In this case, we'll go ahead and use a file system called the WRL. This was kind of an older extension for 3D rendering. It was when people envisioned that browsers would really be a 3D browser. So HTML, which is Hypertext Markup Language, became VRML, or Virtual Reality Markup Language. So we'll just save it like that because it's a nice, easy to read text format, just like HTML is. I'll just save that there, and I'll save everything. And then that way, when I go ahead and I see the file saved, this WRL format, it opens up in a standard Microsoft 3D Builder. And this is what browsers look like when they're browsing in 3D virtual reality. So as opposed to browsing a text document, we're browsing a virtual reality document. So let's take a look at what that document contains. If I open that with, for example, a notepad editor, you can see that it contains a number of prefix information pieces, just like HTML does, but then the individual points in there, X, Y, Z, format are actually written out here. And you can see they're separated by commas and character terms. So all the different points of the seashell, and then the coordinate indices for them, and basically some lighting information, goes ahead and basically defines this virtual reality item, this 3D item, and then it's up to this rendering software to go ahead and draw it. So the next thing we can do is look at how we take points in XYZ format and then project them onto a 2D screen, so that it gives the illusion that that seashell exists just beyond the screen, and we're rotating it around. So that is basically simultaneous linear equations, and we can take a look at that. That's that matrix math that whether Multisim is doing it to solve circuit equations, or this program 3D Builder is using it to project these dots onto a plane. It's all really that same sort of simulation mathematics that we need our engineering technology students to be familiar with. I'm going to stop sharing the screen, and we'll go ahead and proceed with some further discussion of 3D rendering and simultaneous linear equations. All right, thank you very much.
All right, so that's a good starter description of how 3D rendering takes points in 3D space and then goes ahead and presents them on the screen as if it was a 3D object. In terms of the matrix math, I think one of the things that you might be new to you might be this transformation matrix, this idea of a matrix that is used to multiply each of the points of a picture. So for example, a transformation matrix for a rotation. If I want to rotate an object by a certain angle in a counterclockwise direction. So I would create a matrix depending on the angle that I want to rotate all the points of that picture. I would create a matrix that has the cosine and the sine of those angles, multiply it, in this case, by a two-dimensional matrix. So each point of those dots that you saw, and that will be the transformation matrix for that. So you can go ahead and see some example transformations, as well as the matrix that goes ahead and is multiplied by each of the dots. So imagine we have the letter F, and each of the dots in the letter F, as well as the square box that surrounds them, is defined by two-dimensional points. We'll do two-dimensional just to be simpler here. I would use this identity matrix. I would multiply each point by this identity matrix, and they would not change at all. If I want a translation matrix, you see I've added the X and Y translation to this identity matrix. So now when I multiply this by each point, it moves over to the right by X spaces and moves up by Y spaces, and I've basically translated the F, the shape of the letter F has now moved a little bit up to the right. And rotation, the one I mentioned earlier, I have a certain angle theta that I want to rotate the letter F, and I go ahead and I enter the cosine and sines of that angle into a matrix, multiply that by each point of that letter F, and you can see it's now rotated. And of course, there are other shear, reflecting about the origin, reflecting about the x-axis. You might have seen that in video games, reflections, as well as rotations and things like that. So these are matrix math calculations, and they can get pretty tedious to go ahead and program over and over again. The idea that you might want to take an object and rotate it a certain number of degrees is not something that you want to really write the software for every single time. So there's libraries of functions that you can go ahead and call, and these are standardized so that one of them is called OpenGL. So there are other ones. It's not just OpenGL. There's also DirectX, which is a proprietary one for Microsoft Windows. There's also other libraries that you can use to do these kind of transformation matrices and do all this graphics. But OpenGL is a open source version. And for example, we can look up the formula, I'm sorry, I should say the function GL rotate. So if I go to GL rotate, this function here, it says that what you can do is you can give it the angle that you want to rotate in a counterclockwise direction around the origin, and then the X, Y, and Z coordinates that of the point in space that you want to go ahead and rotate, and it'll return the new X, Y, and Z rotated version for that point. And it performs the matrix math, which here is spelled out kind of in algebra. And it will go ahead and handle taking the cosine and the sine and putting that into a matrix. But so this way you don't have to go ahead and perform these transformations and take the sine and cosine. You'll just call this function called GL rotate. And the importance of using a standard library like OpenGL is that OpenGL is supported by these chip manufacturers such as NVIDIA. So NVIDIA makes these chips that will go ahead and accelerate your graphics programming, or let's say make your video game faster. And the idea of mathematics acceleration is useful, but only if I don't have to rewrite my video game for every new kind of hardware. So I want to be able to sell my video game to people who have all sorts of different kinds of hardware. So instead of writing my own software functions for all of those matrix transformations, I'll go ahead and use the OpenGL library, and then I'll understand that the people who make the hardware, like NVIDIA, promise to go ahead and support all of those OpenGL drivers. So if I go ahead and use those functions in OpenGL, I know that I don't have to rewrite my video game for other hardware functions. So OpenGL is, they promise to support it. They also go ahead and make their own extra extensions because they would like you to write your video game so that it certainly only runs on their hardware. That's certainly possible. So for example, Nintendo, PlayStation, Xbox from Microsoft, these have dedicated chips, and all of the video games are written specifically for those chips. It's not possible to take the software for that video game and move it over, for example, to a PC and run it. You would have to change the software, recompile it for that. But you don't have to do that if you're using OpenGL. So that's a great thing that is really driving the industry. As long as you're using this library of functions, you're not inventing your own functions, then at least you know, no matter what the newest chip or hardware from NVIDIA or other manufacturers like AMD, they will support OpenGL. So as long as you wrote your game or your VR, virtual reality, or whatever program using OpenGL, they'll continue to support it. So that's a driving factor. It kind of glues together your software and the hardware that keeps changing year after year. Then
I had a question.
Yes, sir.
Hey, since this video has GL, what do you call it again?
OpenGL is not owned by
OpenGL.
NVIDIA. It's yeah.
If that's their own thing, what's AMD's equivalent of OpenGL?
OpenGL is not owned by NVIDIA.
I see.
OpenGL is just a standard that hardware manufacturers have agreed to support, so that I don't have to write my video game over and over again.
Understood.
Okay, so that's kind of the glue that ties together your video game to all the different kinds of hardware that your customers might buy. So as long as you're using one of these, OpenGL is not the only one. There are other standards that are used. So for example, DirectX is the standard used by Microsoft. So DirectX is a competitor to OpenGL. So you can write your video game on DirectX, and then you'll know it will work on all of the Microsoft products and all the hardware that runs Microsoft Windows. So that's just OpenGL isn't the only standard, but it's one of the ones that allows people to use a library of functions rather than try and invent their own functions. But that doesn't mean that NVIDIA is only going to support OpenGL or only going to support the DirectX from Microsoft or one of the other competitors. They also support their own library, and those are usually used for cutting edge products that haven't yet made it into the OpenGL. So for example, virtual reality is a big frontier that people are exploiting right now with the virtual reality goggles. So NVIDIA is helping support the makers of those headsets and also the makers of the games that are in virtual reality to try and deliver virtual reality experiences. So let's go ahead and take a look at a short video from NVIDIA talking about what is special about virtual reality and why is it more advanced, for example, than just simple one-screen 3D rendering.
NVIDIA has powered the world's highest performance graphics experiences for more than 20 years. Now we're harnessing all of that innovation to deliver the next generation of virtual reality. At NVIDIA, we view virtual reality as the next major computing platform. Like smartphones over the last 10 years, virtual reality will change the way that we do business, the way we enjoy games and entertainment, and the way we interact with friends and family. Every industry, from automotive to medical to architecture to art to gaming, will be changed by virtual reality. From a graphics perspective, there are two major challenges. The first is that virtual reality requires an incredible amount of graphics horsepower, up to 7 times that of a normal PC gaming experience. The second is that virtual reality requires very responsive graphics. When I move my head, the display needs to update instantaneously, within 20 milliseconds, in order to provide a smooth, comfortable experience. NVIDIA is building a powerful computing platform for virtual reality that has 3 major components. First are NVIDIA GPUs that deliver industry-leading performance and are purpose-built for virtual reality. Our new Pascal architecture brings features like simultaneous multi-projection and graphics preemption that improve performance and reduce latency. The second are NVIDIA's graphics drivers, which provide a great out-of-box experience for gaming and professional applications. And lastly, our VRWorks SDK brings a new level of immersion through ultra-realistic graphics, ray-traced audio, precise touch interactions, and physically simulated environments. In addition to our GPU and SDK technology, NVIDIA is creating VR tools and applications that are both fun and productive. Our first virtual reality experience, VR Funhouse, shows off what's possible with our Pascal GPUs and VRWorks SDK in an interactive carnival environment where everything behaves according to the laws of physics. Our Ansel technology allows gamers to capture 360 stereoscopic images and share them with their friends, either on Google Cardboard or a PC VR headset. And our Iray VR technology allows professionals to render their models with ray-traced photorealism and then explore them in virtual reality to get a full sense of space, scale, and lighting. But finding the right hardware for a great VR experience can be very challenging. To help aid this, NVIDIA has created the VR Ready program that helps gamers and professionals identify the right notebooks, PCs, and graphics cards to deliver a great VR experience. We're excited to be enabling the VR ecosystem to create amazing virtual reality experiences and can't wait to see what comes next.
So that's really showing that for virtual reality, using this OpenGL interface, this application programming interface, that's not enough. They would like you to use the GeForce virtual reality VRWorks application programming interface, or API. Now, it does mean that you would be stuck using only hardware from NVIDIA, but with virtual reality, many times vendors such as Oculus have already decided to include NVIDIA hardware inside their goggles. And so they already know the only hardware that's going to come with it is the NVIDIA hardware GPUs. So they're going ahead and willing to use the API from NVIDIA. They're not trying to use an open API. But in the future, as I imagine competition heats up, vendors will insist on an open version so that they can get lower prices by having competing manufacturers make chips to do that acceleration. So that's that VR work. So what is a graphics processing unit? What is this GPU? It's basically a CPU, but one that's specifically designed to deal with graphics. So it has built in a lot of decompression and specific to video hardware, you know, the HDMI cables and the VGA display cables that you'll need to connect to video hardware like video screens and TV sets. But also the specialized RAM that's very fast, and then a large number of these graphical computing engines, so that a problem such as rendering that seashell that you saw in the earlier video can be divided into many small parts. And the math, remember I showed you that math has to be executed for each dot of that seashell in order to rotate it. So you have to find that transformation matrix, and you need to then multiply it by every single dot of that seashell. Well, if I have multiple GPUs or multiple GPU cores on a single chip, let's say I have 10 different cores, then I can go ahead and take you know, a tenth of the dots and send it to each of the cores, and I can get it done much faster because they'll be doing that math all at once. So that's pretty much what a GPU is. You can certainly look up these the history of GPUs over the years. You can see here the GeForce is the one that they were talking about just a moment ago, having to do with right now they're up to the 30 series of GeForce, and you can see compare the different types of RAM that are in there, and then the high end and what the different things that you're getting for your money in terms of the sort of specialized hardware that goes into those chips just to do that math faster. And people are spending quite a bit of money. You can see these chips go upwards of $300 just for the high end there, just to go ahead and do the math faster. And that's really what a GPU is. It's also just a way to go ahead and do the math faster. It's an extra chip besides the CPU. CPUs can certainly add and subtract and multiply and divide, but Intel, for example, Intel Core CPUs, they have maybe 4 cores, so they can do 4 mathematical operations simultaneously, or maybe they have 8 cores if they're a very expensive Intel CPU. But GPUs might have 128 cores. They're much, much simpler than a CPU. They don't do all the things a CPU does in terms of the operating system and handling Windows, but they do the simple things, just taking 2 matrices and multiplying them together, but they can do 128 of them simultaneously. And remember, all of these mathematical operations are just building up of AND and OR and NOT gates, usually just NAND gates, going ahead and creating the exclusive OR, for example, to add binary numbers, and all other kind of operations that an arithmetic logic unit of a CPU would normally do, but these are just much simpler units, but many, many more of them. So another area where we can see math acceleration taking place is with regard to artificial intelligence. And artificial intelligence, just pattern recognition, is moving to the edge. And so what do I mean by that? Well, let me show you what I mean by that. So here is an example of a Jetson Nano 2 GB developer kit. So this is just a small board, fits in the palm of your hand. Definitely can get very hot because it's definitely operating very, very fast. But what it has is it has a GPU, 2 GB of RAM, and a bunch of interface ports to connect to video displays and cameras and the Ethernet. But otherwise, it's a very, very simple system that just does that math acceleration. And the reason why we want to move artificial intelligence to the edge is because we're looking for speed. So first of all, what is artificial intelligence? Artificial intelligence is really just recognizing patterns. So we just want to go ahead and recognize patterns that we observe And to do that, it's literally trained on thousands and thousands of examples. And once it's been trained, then the recognition function, that thing I said, recognizing patterns, that's called inference. So mostly artificial intelligence does involve a lengthy training period, but that's only performed once. Once the system is trained, it's the inference or the recognition function that has to be performed over and over again. So what do we mean by at the edge when we talk about artificial intelligence at the edge? What we mean is we're performing that inference on these tiny computers without having to send all of the data back to the cloud, or without having to send all the data back to your PC, or without having to send all the data back to servers who will perform that. Why? Because when you're driving down the road at 80 miles an hour, you really don't have time to go ahead and send all the camera data to back to the server to go ahead and figure out that you're coming up against an obstacle in the road and you need to hit the brakes. So it is very, very important to do this inference very, very fast. So right now I'll show you a video about ECPI engineering technology demo, and we're getting about 15 frames per second of inference, and we're only using 5 watts of power. So it's very important to be very fast and also very, very low power, because these are intended for mobile devices. So let's watch a short video showing that this is just one that I've constructed, so you'll apologize for the sloppiness of the home lab here, but this is just showing you the inference working at 15 frames per second. So you can see that I'm walking in front of the camera, and it is going ahead and seeing a rectangle, and I'll pause the video for a moment. It's identified with 87.6% accuracy that there is a person standing here, and this green box roughly is the outline of where the person stops and starts. And it is also identified with 95.3% accuracy that there is a chair here, and these roughly represent the bounding rectangle of where the chair is located in the image. So being able to do this at 15 frames per second does require a lot of GPU power. So let's take a look at that a little bit more closely. You can see that the Jetson Nano 2 gigabyte module has 128 of those NVIDIA Maxwell GPUs. That means it can take this problem of looking at a picture and identifying where is the person and where is the chair, and send it that problem, which involves multiplying by matrices over and over again, each points in the picture and groups of points in the picture, and multiplying by these matrices. It can do 128 of these math operations all at once. So having things done in parallel, unlike your Intel CPU that can really only do 4 mathematical operations all at once with its 4 CPU cores, being able to do 128 of them is very important. On top of that, it's included a CPU. So there is a 4-core CPU similar to the one you have in your PC, and that manages feeding this beast, if you will, feeding it with the pictures it needs, and going ahead and outputting, and also providing a user interface, a Windows user interface, running the Linux operating system, all sorts of, I think it's Ubuntu in the case of the one you just saw. All basically meant to leave these alone just to do the math, and then everything else is just done by the more traditional CPU, in this case a quad-core ARM Cortex A57. In addition, there's 2 gigabytes of memory, but that is very fast memory, and it also has the ability for in-between clock cycles for multiple devices to access the same memory. So that way the CPU can go ahead and deliver the next screenshot, and at the same time the GPUs can go ahead and access that same data to do the math without bumping into each other, because it has very, very fast RAM. So this is a typical demonstration. This is we had in the lobby of our campus here. Students were observing this live, They were seeing it execute at 15 frames per second. They saw that we were using a low power, 5 watts of power. So it really just got warm to the touch. But this was the simple device there, and there's the tiny camera here. The rest is just a display and a rolling cart to be able to move it around the building easily. You can see here a little bit zoomed in what's going on, what the students see. Once again, here's the camera, and here's the board, nice and tiny. It's being operated just using a USB just power block here, but it could be battery powered as well. 5 watts of power is something that is definitely manageable with a battery life. Here's a zoom in of the screen, and you can see in one section, once again, 15 frames per second. It's identifying people in the picture, the level of accuracy of identifying the person. It's less sure about this person, probably because maybe there's a plant over here and another person peeking around the corner. So it's less certain about where the rectangle of this person begins and ends, but it's more certain about that. So it's important for artificial intelligence not only to classify objects in an image, but also to express how certain they are that that indeed is what it is that they're seeing. And here you can see some statistics. You can see that for all of those rectangles, it talks about the left, the top, the right, and the bottom of that rectangle in terms of which point on the screen it appears, as well as the width and height of that rectangle and the center of that rectangle in terms of X and Y coordinates. And then also timing in terms of how many milliseconds are being used for each part of that artificial intelligence, pre-processing the image, going ahead and getting that off of the network between the CPU, post-processing the image, creating the visualization that appears on the screen. So basically, it's taken about 78 milliseconds of CPU time, that quad core you saw, and then about 67 milliseconds of CUDA time. Basically, those multiple GPUs, those 128 GPUs I mentioned earlier. So this is the Jetson Nano 2 GB developer kit. You can buy it on Amazon for under $100. So it's very, very affordable in terms of artificial intelligence. We'll be doing more with this project, so keep your eyes open there if you'd like to get involved in that. But you can see that it's a nice development product, because not only does it give you the GPU and the CPU that you need, as well as 2 GB of memory, but also it gives you the working tools you need to be able to load an operating system onto an SD card. It gives you one high-speed USB port and 2 regular speed ISP ports, and then also a device mode. It gives you an HDMI output, which is what we use to provide to the graphical display. And then it gives gigabit Ethernet, a camera, and an expansion header. So we're going basically everything you need to set up this whole CPU on a tabletop, if you will. All you need extra is the SD card with all the software on it, a keyboard, a mouse, and a screen. The software itself is kind of cutting edge. So I'll be perfectly honest with you. It took me several weeks to go ahead and put together that software. A lot of it had to be compiled specific for this type of hardware using the cross compiler method on a different PC. So it's a lot of parts to it. It's not necessarily ready to fly off the shelf, but that's really where we feel that industry is moving, that the industry is looking for faster and faster processing of mathematics. It's looking for cheaper and smaller and less battery life, less battery consumption of that same processing. And it's using that processing for a large number of different purposes, whether it's gaming, whether it's virtual reality, whether it's cryptocurrency mining, whether it's artificial intelligence. We feel that this is moving in the direction that's going to impact your career. That's why EET 310 is an important class to take, so you understand some of that ways that matrix math, like Cramer's rule, goes ahead and accelerates simultaneous linear equations, but also transformation matrices like you saw today. And then also we think that in the particular with regard to artificial intelligence, more and more the artificial intelligence will be moved to the edge. In other words, the actual device where the action is happening is the one that will have to perform some analysis of the data, like the artificial intelligence here, where it's showing where people are located. Because in a manufacturing environment, artificial intelligence like that could go ahead and see where people are walking around on the factory floor and might take actions for safety purposes to slow down, let's say, artificially intelligence controlled forklifts that know when a person is in the way, and they know to slow down and then stop to avoid collisions. So that kind of extra smarts, I'll be having another lecture series on the types of use of artificial intelligence. You probably have already encountered it, but we're seeing more and more of that taking place at the edge, rather than having to send all the data back to the server to go ahead and figure out where people are located. It's just too slow to send that massive amount of data, high definition video, back to the server and then come back. You'll never be able to do it at 15 frames per second. And even 15 frames per second is too slow for a vehicle moving at, at highway speeds. So you'll see even faster computing, but once again, in the vehicle itself, or in the robot itself on the factory floor. And that's kind of where ECPI University and myself personally, I see the direction of this technology going. So I wanted to give you this brief overview so you kind of have a sneak peek of where your career might be going. I'm not saying that you're going to necessarily work in video gaming or work in virtual reality or work in cryptocurrency mining or work in artificial intelligence. But even if you don't work in any of these areas, you can see how it will impact your engineering career and these kind of trends where people are accelerating the mathematics. They want to be able to use different brands of hardware. So they want standardized libraries to go ahead and be able to use their software on multiple kinds of hardware. And they want that hardware to be fast, small, and low power. Those are trends that I think are going to definitely impact your future career. So I know it's not necessarily part of your EET 310 curriculum, and I appreciate you taking the extra time to either watch this live or go ahead and look at this video later on. Hopefully it's of interest to you, and I appreciate you taking the time to listen in today.